I'm Mark Baumann, and I'll be talking about aiming at Proxima Centauri b. This will be an analysis of relativistic spacecraft trajectories. And can we get the slides up, please? Thank you. So when I say relativistic spacecraft, what I mean is a spacecraft that is traveling at a significant fraction of the speed of light. An example might be something like what we've talked about earlier today, a laser-propelled spacecraft, something that has the mass of a gram, a spacecraft on a chip, basically, that includes sensors and communications and a nuclear fission battery. And you attach it to a gram-scale laser sail and accelerate that using a 70 gigawatt laser array. In about 9 minutes of shining this laser on the sail, you can accelerate it up to 20% of the speed of light. That's about 15,000 Gs of acceleration. It carries no propulsion or propellant of its own, and that's important for a couple of reasons. One is that it allows it to be very small, which enables us to accelerate it very quickly because it has very little inertia. And also, that means it has no propulsion of its own, so it will not be able to course correct. Or at most, it could do some minor course corrections using a photon thruster. So the question we are asking is, how do you aim such a thing? What is the trajectory of a relativistic spacecraft that makes the voyage to some interstellar neighbor unaided, aside from some minor course corrections? And if we look at the scenario that we have here, we have an object, which is the spacecraft, moving at a significant fraction of the speed of light, and it's subject to the gravitational effects of multiple bodies. This is a job for relativity. When I say relativity, I am talking about the general theory of relativity, which is Einstein's geometric model of gravity, in which matter causes space-time to curve, and in the words of John Wheeler, matter tells space-time how to curve, and curved space-time tells matter how to move. That's the idea in a nutshell. And general relativity is needed when we have objects moving at a significant fraction of the speed of light that are subject to gravitational effects, which is exactly what we're talking about when we talk about a relativistic spacecraft. The thing about general relativity is that Einstein's equations are very complex and difficult to solve. Einstein's equations consist of 10 coupled nonlinear partial differential equations. They are solvable computationally. It's been done, but it's very computationally expensive, and it's very difficult to do. So what we have done is we are using an approximation to general relativity that is appropriate in this scenario. And so I'll talk about our methodology. There are different approximations to general relativity. Post-Newtonian and Post Minkowskian are two of them. Both of them are power law expansions of the gravitational field, in which you start with the zeroth order approximation, which is flat space, no gravity at all. And then you introduce higher and higher order terms. The more terms you introduce, the more accurate your approximation. Post Minkowski in particular is an approximation where you expand the field in powers of g, Newton's constant. And the Post Minkowskian, or PM, model of gravity can handle fast motion, but only for weak gravity. So what do I mean by fast motion? I mean bodies moving at a significant fraction of the speed of light. And by weak gravity, I mean far from the short shield radius, the short shield radius being the radius of the event horizon of an object. So weak gravity works well for stars and planets because they are much larger than their short shield radii. but it doesn't work well when you're talking about black holes and neutron stars because they have sizes that are comparable or smaller than their short shield radii. So what we use is the first order G, first power of G, Post Minkowskian model of gravity. So in 2008, Ledvinka, Schaefer, and Bichak derived this Hamiltonian. I'm not going to go through it. I just wanted to show it to you that it's quite complex. Has many, many terms. This is all inside of a sum. But they derived this Hamiltonian, which is the energy function of a system. It's the total energy of a system, kinetic and potential energies. And when you have a Hamiltonian, what you can do with it is you can put it into Hamilton's equations, which I have pictured right here. And you see that H appears in a derivative on the right-hand side of Hamilton's equations. So if you can take the derivative of this Hamiltonian here and put it into Hamilton's equations, then you have a model for doing dynamics in post-Minkowskian gravity, which is what Justin Fang, who's in the audience, and he's speaking on Wednesday, and I and our collaborators did in 2018. We developed a numerical solver that does post-Minkowskian gravity. And we call that solver Pullman, which stands for post-Minkowskian n-body solver. So Pullman can handle any number n of bodies interacting gravitationally, and it handles the fast motion regime. And it even handles photons. It's open source. It's available on GitHub. Version 1 we wrote in C, and version 2 we wrote in Julia. Julia is a scientific computing friendly language. It has state-of-the-art differential equation integrators, which are optimized for processor architecture. It does automatic interpolation of discretized solutions to your differential equations that you've solved. It has automatic differentiation, which I'll come back to in a minute. But basically that allows you to differentiate any coded function. Any function in your code can be differentiated using automatic differentiation. And it includes high-precision floating point types. So it's a great language for doing scientific computing. So the first question we asked so Pullman is our methodology, and the first question we asked is, what's the influence of each gravitational body on the spacecraft's trajectory? So here's our setup. For a target, we use Proxima Centauri b. You could use any target. We chose Proxima Centauri b because it is the nearest star system, Proxima Centauri, and it's a terrestrial-sized exoplanet in the habitable zone. It's about 4.25 light years distant, which is about a 21-year journey if you're going at 20% the speed of light. And we considered the influence of these bodies here on the spacecraft's trajectory. So Sun, Earth, Moon, Jupiter, Mars, Proxima Centauri itself, and then Alpha Centauri A and B. For Alpha Centauri A and B, we used the barycenter and treated it as a single object. So the spacecraft itself is a test particle, which means that it experiences gravitational forces, but it does not produce a gravitational field of its own, which is a fair assumption because it is only 2 grams. And its initial position is 0.1 AU in the direction of Proxima Centauri. So why 0.1 AU? These graphs here come from Parkin 2018. This is in particular about Breakthrough Starshot, but this could apply to any relativistic spacecraft, but this one in particular that we looked at is Breakthrough Starshot. Here you see the distance from Earth after the acceleration phase. It ends up at about 0.1 AU after the acceleration phase has ended. These other charts show you the speed of the spacecraft approaching 0.2. Down here, by the way, the horizontal axis is in minutes. So you see that the acceleration phase is about 9 minutes. Here you see the acceleration starts out at about 15,000 Gs of acceleration. I like that Parkin put that the Laniakea supercluster escape velocity on here. It's kind of an interesting thing to think about, that the spacecraft at that speed is not only going to escape the solar system, it'll escape the galaxy, it'll also escape the local group, and it'll also eventually, given enough time, escape the supercluster, the galaxy supercluster. So we started at 0.1 AU from Earth in the direction of Proxima Centauri. So to find the gravitational influence of each body, what we do is we start with a naive initial velocity, which is aiming the spacecraft at Proxima Centauri b, where it will be at the time of closest approach. That aiming problem is an interesting problem in itself, which we solve in our paper. But this is in the absence of gravity. If you just aim at where it's going to be, naively. And then you introduce one gravitating body at a time, and you see, you calculate the trajectory as a result of having that gravitational influence, and you see how much you miss the target by. The more you miss the target by, the bigger influence it had on the trajectory. So that was our way of measuring the influence of each body. And you can see that the sun had by far the biggest influence. The sun caused the spacecraft to miss by 0.139 AU, about 20 million kilometers. Jupiter was the next biggest influencer. And then this is sorted in order of influence, decreasing influence. You can see that the Moon and Mars had very little effect at all. Proxima Centauri itself also had a surprisingly small effect on the trajectory of the spacecraft, and we attribute that to, first of all, Proxima Centauri is not very massive. It's 0.1 solar masses. And Proxima Centauri is at the end point of the trajectory, so the spacecraft never actually, in trying to hit the target, hasn't flown past the target yet. So the target hasn't had time to deflect the spacecraft's trajectory yet. But it does have an influence, so we kept it in our simulation. We dropped the Moon and Mars from the simulation because their effect was negligible. So what that leaves us with is 6 bodies. And the next problem we focused on with these 6 bodies in the simulation is the targeting problem. This is kind of the real question that we started with was, what initial velocity vector do you have to give the spacecraft in order to hit the target dead on? So we included the 6 bodies that I mentioned: the spacecraft, Sun, Jupiter, Earth, Proxima Centauri, and Alpha Centauri AB, barycenter. And you start with an initial guess at what would get you there. You compute the trajectory, and you compute the miss vector, how far you miss it by. And what we wish to do is we wish to find the initial velocity that produces a miss vector of 0. So this is it in a schematic here. So we have this solver here, this iterative differential equation integrator. We provide an initial velocity vector, and the solver produces the miss vector. And what we want to do is we want to find what input produces an output of 0. So that's a familiar problem. That's called a root finding problem. And so we use a Newton-Raphson type root finding method to solve this problem. So Newton-Raphson type method works something like this. You have a function f of x, and you're trying to find the root of the function. We're trying to find where it crosses 0. You start with an initial guess, x naught, and you look at the derivative of the function at that point, and that gives you the tangent line, which you follow down to 0, and that'll give you your next guess, x1. You look at the function's value here, you find its derivative at that point, which gives you another tangent line, which you follow down to give you your next guess, x2, and then you'll look at the derivative here, and you get another tangent line that you follow down to 0, and you keep doing this iteratively until you find where the function crosses 0. So that's Newton's method in a nutshell. And what we did is we used Newton's method on our integrator here using automatic differentiation. So automatic differentiation is a modern marvel of scientific computing, in my opinion, because it can take the derivative of any black box function. In this case, our black box is this iterative integrator, which performs hundreds or thousands of iterations using a 9th order Runge-Kutta style differential equation integrator. And in this case, we use one called Werner's method. So that's the black box, and we are taking the derivative of that. So the fact that that is even differentiable to me is remarkable. But we can do it, and we were able to use Newton's method to find the input that produces an output of 0. So that allows us to hit the target. And we were able to hit the target with arbitrary precision, so down to machine precision. Now, this is all within a given model of gravity. I'll talk about that some more in a minute. But we call this our fine-tuned initial velocity vector. So in this case, using the Post Minkowski model of gravity, we were able to hit a target at a distance of 4 light years with a precision of a femtometer, which is the size of an atomic nucleus. So like I said, arbitrary precision. Now, this is not taking into account the errors that could be introduced by your model of gravity. So that's the next thing I want to talk about. So first of all, what if you used Newtonian gravity as your model of gravity? So we did that. We used our fine-tuning method with a Newtonian model of gravity to get the initial velocity vector of the spacecraft. We then ran that initial velocity vector through our simulation to compute the trajectory, but this time taking relativity into account, because our simulation uses Post Minkowski and gravity, so it takes relativity into account. And we found that the missed distance was about 690,000 kilometers. So that's nearly twice the Earth-Moon distance. So if you use Newtonian gravity to plot the trajectory of your spacecraft and you neglect relativity, then this is the best that you'll do. You'll miss it by about 690,000 kilometers. So relativity is necessary. If you have a relativistic spacecraft, something that's moving at a significant fraction of the speed of light, you must take relativity into account in order to accurately plot the course of the spacecraft. What about Post Minkowski and gravity? That's the model that we're using. What's its accuracy? So we're using a first order Post Minkowski approximation to general relativity. So that's to the first power of Newton's constant. If you include the second order term, the g squared term in the power series expansion, you would have second order Post Minkowski approximation, which is a better approximation than the first order. We can estimate the contribution of the g squared terms using analytical scattering formulas from general relativity. We derive these scattering formulas in our paper. But using the analytical scattering formulas to give us an estimate of the error, we found that the sun caused a deflection of about 30 kilometers. And again, the sun was the biggest impactor on the trajectory of the spacecraft. And it causes a deflection of 30 kilometers. So that is going to be your best case when you're using Post Minkowski and gravity. Now, considering that the target is the size of the Earth, 30 kilometers error is acceptable, I think. So, we, from that, conclude that Post Minkowski and gravity is sufficient as your model of gravity for plotting the spacecraft over the trajectory of a relativistic spacecraft. Lastly, we considered errors in the initial launch vector. So what I've talked about so far is in the ideal launch case where we know what our target is. We figured it out using this fine-tuning method that we've developed. We know what our initial velocity vector should be, but what's the guarantee that we're going to hit that initial velocity vector perfectly? What if there's an error in the launch itself? So we considered that as well. So consider an error theta max in the initial vector. So that error theta could be due to any error during the launch or the boost phase of the spacecraft. So what we did is we constructed a disk around the target that has a radius corresponding to the error theta max. We choose random points on that disk to be our new targets, and then we compute the trajectory hitting those new targets that are missing the main target by up to an error of theta. And then we did that 200 times for each theta max and took some statistics of that, and we found that, for example, if your initial vector is off by 1/1,000,000 of a degree, you'll miss by 465,000 kilometers, which is about the, again, we're in the ballpark of the Earth-Moon distance. So very sensitive to errors in the initial trajectory, the initial velocity trajectory. Okay, so in conclusion, we found that the sun has the largest impact on an interstellar spacecraft trajectory. Using our Pullman methodology and a route finding method, we developed a process for finding the initial velocity vector that will make a direct hit on your target within a given model of gravity. If you use only Newtonian gravity and neglect relativity, your miss distance for Proxima Centauri b, 4.25 light years away, will be at least 690,000 kilometers. Post Minkowski gravity is a suitable model to use in place of a general relativity with errors up to only 30 kilometers. And we found that random variation in the initial angle can lead to miss distances of about the Earth-Moon distance if your initial vector is off by an angle of 1/1,000,000 of a degree. So thank you for your attention. I'd like to thank my co-authors, Justin Fang and Nikki Isak. I'd also like to acknowledge Al Jackson and Richard Massner for inspiring this project. You can find me online at markbaumann.net. Any questions? Thank you.
So this was for Breakthrough, right? Or for the Breakthrough case, I guess. The question is...
That was our test case, yeah, our proof of concept case, yeah.
So, how does 1/1,000,000th of a degree, line up in terms of what that would be capable of, or your ability to sense that you are 1/1,000,000th of a degree off?
That's a good question. I don't know what the engineering challenges are in that. I'm not an engineer. I'm a physicist. I worked on the trajectory problem more than the launch problem. So I can't really speak to what the engineering challenges would be there, but I imagine that they are very significant in order to have your accuracy better than 1/1,000,000th of a degree. Because if you're even just 1/1,000,000th of a degree off, obviously, like I said, you're going to miss by the ballpark Earth-Moon distance. So that's not very forgiving. Yeah.
When you say second-order gravitational effects coming from the sun, what does that mean in sort of a physical sense? Is that perturbations from, asymmetries within the sun, or like what does that translate to in a sense for what is going on inside the sun?
So when I talk about second-order effects, I'm talking about the effects that the sun has on the space-time around it. And a zeroth-order effect would be no effect on the space-time around it, so that would be flat space. First-order effects would include some curvature of space-time. Second-order effects would be more precise estimate of the curvature of space-time due to the sun. So really what we're talking about is the curvature of space-time due to the sun and approximating that with higher-order effects. That's what I mean by second-order effects. Yeah. Mm-hmm.
This issue of navigational accuracy comes up frequently. It's on my frequently asked questions list that I talked about earlier this morning.
Yeah.
So 1/1,000,000th of a degree is beyond what we can presently do, with astronomical observatories and so on. But the spacecraft would have the ability to navigate, right? And this has already been demonstrated on the New Horizons spacecraft. So New Horizons has detected the parallax shift of Alpha Centauri and other stars as it's moving out into the galaxy. And they've demonstrated that it can measure its position using measurements of parallax like this sufficiently accurately to do interstellar navigation. So we can't send things that accurately, but en route, they can sense their position accurately enough to do the navigation that you've laid out very nicely. I mean, you've given us the tools, and New Horizons demonstrated that it can measure its position accurately enough to do what needs to be done.
Yeah, thanks for that comment. And I think this is a good demonstration that course correction is going to be needed for a spacecraft like this. And I think it's exceptionally interesting that the spacecraft can guide itself, navigate itself using the stars. You know, it's like the sailing ships of old, you know, but now we're talking about interstellar travel. But yeah, I agree with you. I think that course correction is going to be required because to achieve that degree of accuracy and launch is going to be extremely difficult.
When you talk about the sun or the earth or something like that, what model of the sun are you using? Are you saying that the sun is just a point source of gravity?
That's right.
Or the earth, and both of those statements we know are false. How sensitive are you to what the actual shape of the sun, the earth, or whatever the other sources that you're using are?
Yeah, that's right. We were treating all of our gravitational sources as point masses. I think if you're sufficiently far away from the point mass, that that the Post Minkowski model of gravity is still effective. And in this case, we're an AU away from the sun and 0.1 AU away from the Earth. So I think those are significant enough distances for the Post Minkowski model to work well. But it's true that we are making an approximation by treating them as point masses. Yeah. Thank you.